This video is brought to you by mywayteaching.com.
So in this standing waves and normal modes, you can see in the figure here, it shows a stationary wave pattern resulting from superposition of two traveling waves in opposite direction. Okay, so here we have considered the two waves which are traveling in opposite direction and the superposition of those two traveling waves, isn't it? These are all the stationary waves. See, the most significant feature of stationary wave is that the boundary conditions constrain the possible wavelengths or frequencies of vibrations of the system, which means the system cannot oscillate with any arbitrary frequency. It is characterized by the set of natural frequencies, or we can say normal modes of oscillation. It is characterized by a set of normal modes of oscillations or natural frequencies. See, let us determine these normal modes for a stretched string which is fixed at both ends. Okay. The position of the nodes when amplitude is 0 is given by sin kx is equal to 0 from the equation that we studied, yx comma t is equal to 2a sin kx cos wt, which implies what? Kx is equal to n pi, where n can be any number 0, 1, 2, 3. So we also know that k is equal to 2 pi by lambda. We get x is equal to n lambda by 2, where n is equal to 0, 1, 2, 3. It goes on. So clearly the distance between any two successive nodes is lambda by 2. It can be distance between two nodes or distance between two antinodes. You can take any one. In the same way, the position of antinodes where the amplitude is maximum, antinodes means the amplitude is largest, are given by the largest value of the sign, because antinodes have the maximum amplitude. So largest value of sine is 1, isn't it? So sin kx is equal to 1. So which implies kx is equal to n plus 1 by 2 into pi, where n is equal to 0, 1, 2, 3, and it goes on. Okay. Again, the distance between any two consecutive antinodes is lambda by 2, as I told you. The equation, that is x is equal to n lambda by 2, can be applied in case of a stretched string of length L which is fixed at both ends. We'll take one end to be at x is equal to 0. The boundary conditions are that x is equal to 0 and x is equal to L. These two are the positions of node. The x is equal to 0 condition is already satisfied. X is equal to L node condition requires that the length L is related to lambda. So L is equal to n lambda by 2. So the possible wavelengths of stationary waves are constrained by the relation. With from this equation of L, we can get the equation for lambda, which is equal to 2L by n, where n is equal to 1, 2, 3, and it goes on. So using this equation, we can also get, so we can write the corresponding frequencies as nv by 2L, where n is equal to 1, 2, 3, and it goes on. So we have thus obtained the natural frequencies, the normal modes of oscillation of the system, the lowest possible natural frequency of the system. We call it as fundamental mode or the first harmonic. Okay. Lowest possible natural frequency of a system. So we call it as fundamental mode, or even we call it as first harmonic. So for this stretched string fixed at either end, it is given by V by 2L, corresponding for n is equal to 1, isn't it? And here V is the speed of the wave, which is determined by the properties of the medium. For n is equal to 2, it is called as second harmonic. And for n is equal to 3, the frequency is called as third harmonic, isn't it? It goes on. We can label the various harmonic symbols by Vn, where n goes from 1 to 3 continues. Okay. You can see this figure. It shows the first 6 harmonics of a stretched string, which is fixed at either end. This is, see, you can see for the two ends of the string, and it is fixed at either end, and these are the first 6 pairs of the stretched string. Okay, a string need not vibrate in one of these modes only. It can take some other forms also, not that only in these 6 modes it will work. Generally, the vibration of a string will be a superposition of different modes. Some modes may be more strongly excited and some may be very less. You know musical instruments, right? Like sitar, violin. So all these, they work on the same principle only. Okay. Where the string is plucked or bowed, and that determines which modes are more prominent than others. So now let us consider normal modes of oscillation. Okay. of an air column with one end closed and the other end open. In that case, a glass tube partially filled with water illustrates this kind of system, isn't it? In that one end is closed and the other end is open. The end in contact with water is a node, while that open end is an antinode. At the node, the pressure changes are largest while displacement is minimum. Whereas at the antinode, at the node pressure change largest and amplitude is zero at the node. We know this also, right? Similarly, when we consider antinode, it is just the other way, which means at the antinode it will be having least pressure and amplitude at the antinode will be maximum. So taking end in contact with water, we'll consider that end at x is equal to 0, the node condition is satisfied. If the other end, if you consider x is equal to L, that is an antinode. Then we can write the equation L as n plus 1 by 2 into lambda by 2. We know this, isn't it? For n is equal to 0, 1, 2, 3, it goes on. And the possible wavelengths are then restricted by the relation, that is lambda is equal to 2L by n plus 1 by 2. Again for n is equal to 0, 1, 2, 3. The normal modes or the natural frequencies of the system, we can write it as V n plus 1 by 2 V by 2L. Again this n it goes on. If you consider the fundamental frequency, at that time we put n is equal to 0, so we get V by 4L. The higher frequencies are odd harmonics, or we can say odd multiples of the fundamental frequency. It can be 3V by 4L, higher frequency, 5V, it is odd harmonics. Higher frequencies are odd harmonics. Okay. This figure, it shows the first 6 odd harmonics of air column with one end closed and the other open. You can see this is fundamental, third, fifth, and this is the 7th harmonic, 9th harmonic and 11th harmonic. So this is an example, or you can see in this figure. It is then easily seen that an open air column at both ends generates all harmonics. Okay, if both the ends are open, then that generates all odd harmonics. That also you can see in the figure. You can see in this figure. Okay, the both the ends are open, it produces all the harmonics. We already know what is resonance is. When the system shows resonance, when external frequency is close to the natural frequency, isn't it? Okay, when external frequency is close to natural frequency, the system shows resonance. Normal modes of a circular membrane rigidly clamped to the circumference, as in the tabla, we see it in tabla, are determined by the boundary condition that no point on the circumference of the membrane vibrates. See, estimation of the frequencies of these normal modes of the system, it's little bit complex because that involves wave propagation in 2 dimension and all. So this is about the standing waves and normal modes.